started. Okay, guys. So we'll start with caches, like a general overview of cache, and then we will move on to mapping. We'll learn about hits and misses, how cache memory is accessed. And then we also have this one separate topic called DMA that we also will go through that. So we'll start one by one. So I'll start presenting now. Is my presentation visible?
Yep.
Yeah.
Okay. So, okay, we'll start with cache memories. So, cache memories are basically a very small amount of memory. It is going to be fast. Why? Because most of the times it is very close to the processor and on the processor. So, how is cache memory fast and how is it, on what principle does it work? So it works on the principle, as Dhanya told, it works on locality of reference. What the words seem complicated. So what does this basically mean? So when we take a program is basically a set of instructions, right? So we have this sequence. We have the first instruction, second, like in a C program, we'll give the main, then we initialize the variables. We have this particular order in which we write the program. But then when the compiler does its job and later when the processor executes the instructions, the sequence is rather different. It's not how we give the sequence. So in each program, only a repeated instruction set gets processed again and again. This is what we call as a localized set of programs out of the localized set of instructions out of the whole program. How does this work? So after analysis of uh, multiple programs, they have come into conclusion of two localities. We have temporal locality and spatial locality. As you can see here, temporal locality is temporal. Here we refer to time basically. So this is with the assumption that when an instruction is used at T1, that's time 1, it is probably going to be used in T2 as well. That's temporal locality. It's an assumption, obviously. It is not how it works every time, but then this is most likely to happen. That's how temporal locality works. And spatial locality is based on the sequential processing of instructions. Basically, if my nth instruction is processed now, it is more likely that my n plus 1th instruction is going to be asked next. This is what spatial locality is. Is temporal and spatial locality clear, guys? Can I get a thumbs up or anything? Is it fine? Was it clear? Okay. So how does this work on the cache? So first, how is this implemented in the cache?
One
First,
second.
temporal. Yeah.
Harish wants you to repeat temporal.
Oh, okay. Temporal. Uh, temporal, as I told. Uh, for example, let's take a loop. It's going to run multiple times. So if this loop is very nearby to my processor, I can reduce a lot of time by not going back to the main memory again and again because it's the same instruction. I want the same instruction to be processed multiple times. That's what I mean by temporal locality. In at time T1, I am processing that instruction, and time T2, I am processing that instruction again. So if I bring this instruction close to my processor in the cache, I am going to reduce a lot of time by not going back to the main memory again. So it's the time, how time acts as the reference. When the instruction is asked at another instance, so that we keep it close by. I might need it again. It's the same instruction, so I'm keeping it close by. That's what I mean by temporal locality. Is it fine now? I am sorry, guys. I am switching between slides. I'm not able to see. Okay. Um, okay. So how is this implemented in the cache? With this, it will be more clear. So in the cache is closer to the processor. So it's basically like taking your ingredients for cooking and keeping it close to you before you start the process. That's what a cache is in general. Obviously, not accurately to the reference, but it's a general idea. So for temporal locality, I take my frequently used instruction and I'll put it in my cache. So whenever I need it, I'll access it from the cache only with a very less access time rather than going back to the main memory to fetch it every time, even though it's the same instruction. That's how temporal locality is implemented in the cache. As for spatial locality, if the processor asks for a particular instruction, I will not bring only that instruction to the cache. Rather, I'll bring the instructions that are closer to the required instruction. So basically the ones above and below. And to this set of instructions, we call it as a block of memory. So that now I do not bring only one instruction from the main memory to the cache. I will bring a set of instructions called as block from the main memory to the cache. So now, whenever I want the next instruction, I want the n plus 1th instruction, I won't go back to the main memory. I will rather get it in the cache. So this is how a cache works. Is this fine, guys? Now it's clear? Okay. So now we'll go to all of this is like basically refers to what a cache is. And what's a cache hit and cache miss. We'll now go to, wait just a minute. I did not order the slides properly, so I'll be going back and forth. So, okay. Now we will see how things are written and read in a cache. Basically, a cache hit and a cache miss. So the order I am going in is based on Carl Hamacher. So if you guys are referring to the textbook, whatever I am saying will be in order. Okay. So now we'll see cache hits and cache misses. So basically, a hit is nothing but I go after I get the instruction from the processor, I go to the cache. If I find that instruction there, it is a hit, or else it's a miss. That's all. It's very simple. Now, when it's a read operation, okay, I go to the cache. I don't find it there, right? Sorry, it's first we will discuss on hits, then we'll go to miss. So basically, I go to the cache, I find the instruction because it's a hit, right? So I'll read that instruction and I'll take it to the processor. It's very simple for read. But when it's write, uh, I'll get the instruction where to write the address. I'll go find it in the cache. Now there are two ways. I can either modify it only in the cache, or I will modify it both in the cache and then go to the memory, main memory, and then modify it there as well. So when I modify it only in the cache, it's called as write back. And when I modify it both in the cache and in the main memory, it's called as write through. So how does write back even work? What is the use if it's only updated in the cache? So what happens is that uh, obviously that instruction has temporal locality. So I might need that instruction again and again. So if let's consider a value that is being updated multiple times, not just once. If I use write through, which is updating the value both in the cache and the main memory, and I am updating that variable multiple times, now I have to go to the cache, write that, go to the main memory, write that. Now I change the value again. Again, I have to go to the cache, change that, go to the main memory, change that. Now, if you see this, there is a lot of time wasted in this. So when we do write back, what we do is we change it only in the cache. No change is done in the main memory. So but then Obviously, we cannot leave it like that because the value is changed in the cache. We cannot leave it just like that in the main memory. So what we do is, uh, when we use a separate bit called as a dirty bit or a modified bit. Basically, what happens is whenever a write operation is given to the cache, we do the change in the cache, only in the cache, and then we set this dirty bit to 1. So that now we know that in this block, there a change has been done. So now after some time, when this instruction becomes outdated and we no longer leave it in the cache, we are going to kick out that block. When we are going to kick out that block, that's when we will update the value in the main memory. So now if I change my variable like 10 times, we only change it 10 times in the cache and we change it only once in the main memory. Now a lot of time is saved through this. But write back also has its own uh, disadvantages. That is, when you change only one word of a block and your block has like multiple words, you have to rewrite all the words of the block. That's one disadvantage of your write back. But then only write back is used predominantly. Okay. This is with introduction to cache, cache hits, and now I cache hits is done. We still have miss. I forgot that. So for a miss, we go to the we'll see for read first. So I want to read something from the cache. I go to the cache. It's not going to be there, right? So now I'll go to the main memory. I'll go to the main memory, uh, and I'll fetch that instruction from the main memory. Now I have two ways. I can either go directly to the processor or I can go to the cache, give that instruction there, then send it to the processor. So we have two ways of doing this. So the first way, the main way is to bring it to the cache because we might need it again. So while when it's a miss, we go to the cache, it's a miss, we go to the main memory, fetch the instruction, bring it back to the cache, then to the processor. But you can also bring it directly to the processor, and that is called as load through. It's not given in this PPT, it's there in Carl Hamilton. So I'm just mentioning it here. Maybe note it down somewhere. I'm sorry I could not make anything ready. But yeah, it's called load through when you bring it directly to the processor without bringing it to the cache. What disadvantage this has is it makes the circuitry more complex because again temporal locality is not served here. So but again it saves some time because we do not go to the cache and come to the processor. So that is for cache hits and miss. We will see one problem regarding cache miss. I'll just show it here. Is this visible, guys? I am really sorry. Can someone unmute because I cannot come back to the
Yeah,
screen?
it's visible. It's visible.
It's visible? Okay. So this example is also discussed in Carl Hamilton, but I just wrote it simply. So we'll assume, okay, we have a cache access of uh, t seconds and main memory access of 10 t seconds. So it's 10 times, okay. Now a cache miss occurs, okay. So we have to go to the main memory, bring the required instruction along with its block. Obviously, we cannot move just an instruction. We are going to bring it as a block to the cache. So, and then the required instruction goes to the processor. Now we have to calculate the miss penalty. That's our question. So, first we go to the cache. So, it's a miss. So, 1T happens. And then now we go to the main memory and we have to bring 8 instructions, not just one instruction. But then there is a pipelining that occurs. So the first word is going to take 10T and rest of the 7 instructions are going to take only one cycle. So it's going to be 70. And then after bringing it to the cache, the required instruction has to go to the CPU or the processor. So that will take 1T. So the main miss penalty is calculated as first cache miss plus bringing the first instruction from the main memory and the rest of the 7 instruction through pipelining. So it takes one cycle each, and then we bring the required instruction from the cache to the processor. That takes 1T. So this becomes 90. So this is a very usual miss penalty questions. So maybe noted, and it is there in Carl Amateur. You can look at it. I will also share these so you can look at it later. Okay, now we are done with cache hits and cache miss. Now we can go into mapping. Okay, yeah, then yeah. Okay, we will start with direct mapping. So first of all, what is mapping? Mapping is basically your process. Okay, wait just a minute. Is this clear, guys? Is all of this clear as of now? Anything I have to repeat as of now? Okay, so we will proceed with the next things. Okay, uh, mapping. So what is mapping? So basically, your processor only knows that there is one memory. It does not know there is like multiple levels of memories. We have a cache, we have a primary memory, we have a secondary memory, all that. Uh, Wait, have I stopped sharing? Okay, wait. I'm really sorry. Okay. Is it fine now?
Yep.
Okay. Okay. So, where did I leave? Yeah, the processor does not know there's multiple hierarchies of memory. It only knows there is one memory. So, your processor basically is in this delusion that we have this powerful computer with the size of hard disk and with the very small access time of cache. Obviously, that's ideal, but that's not the case. So that's what it thinks. And it gives all of its address instructions with accordance to the main memory, with the bigger memory, right? And we have to somehow fit in the main memory addresses into the cache, which is going to be small. So we must know how to map and how to place each block of memory from the main memory in the cache. That's mapping, basically. Okay, we are going to map the memory in main memory into the cache. That's what we are going to do. And we have multiple ways of doing it. And we'll start with direct mapping. Direct mapping is very similar. It's basically hashing. It is literally hashing. It has nothing more. Now we'll consider this example, okay, to make things easier. We'll consider a main memory of 16 blocks, and each block has 4 instructions, okay. So 16 into 4 is 64. We have 2 power 6 instructions basically. So since it's 2 power 6, each address will have 6 bits. Okay, is this clear? Is this calculus? Guys, please, someone please unmute. I cannot switch my window.
Yes, clear.
Okay. Um, so yeah, so it has 6 bits. And now we can leave the last 2 bits because it is going to tell us which instruction of the block it is going to be. Why do we leave this? Because no matter what the instruction is, the whole block is going to be mapped. So we do not really care it's the first instruction or the third instruction. We do not care because even if I call the third instruction, the whole block is going to be mapped. So we leave those 2 bits. Now we have a 4-bit binary number or address, and we consider a cache of 4 blocks. Okay, it's smaller than the main memory. So we have to map it into 4 spaces basically. So the map function becomes a 4-bit address modulus 4 because the space in the cache is 4 in terms of blocks. Because we left instructions, we are only talking in terms of blocks now. So 16 blocks, so we have 4-bit binary. Okay, I think it's clear. Now 4 is going to be 2 power 2. Simple, right? So basically you can actually convert this 4-bit binary to decimal, then apply the mod. But if it's binary, it's actually pretty easy, because whatever is the 2 power, like if it's 2, then the last 2 bits are going to be your answer. It happens every time. So how many ever bit binary you have, if your the second operand in the mod is in a power of 2, the last power bits of the binary is going to be your answer. Basically, if the power is 2, the last 2 bits. If the power is 3, the last 3 bits. That's going to be your answer of the mod. So uh, now in my 4 bits, now it's mod 2 power 2, right? So the last 2 bits are going to give me the place in which the block from the main memory is to be mapped in the cache. Uh, and then we have remaining 2 bits that is going to differentiate the each block. Wait, I'll show an example. It will be clear afterwards. So if we see here, this is 0, 4, 8 and 12. Okay. If you see, the 2 bits are same for all the 4. So basically 0, 0 is 0, right? So all of these 4 blocks is supposed to be placed only in the 0th block of cache. But how do we differentiate all of the 4? The rest of the 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. These differentiate which of the 4 blocks. Now basically, if I get 1, 0, 0, 0, okay, from the processor, I'll go to the CPU. 1, 0, 0, 0. So the last 2 bits are 0, 0. So I am obviously going to search in the 0th place of cache. I'll go basically, wait. Uh, So I'll go to the 0th block. Okay, I am now in the 0th block. But I don't know whether it's the 0th block, 4th block, 8th block, or 12th block that is present in the cache, right? So I will then compare. Now what I got from the processor was 1000. But if in my cache it was 0100, I know it's a cache miss. I'll go to the main memory. But if it was 10 other, if the tag was 10, then it's a hit. So this is how so basically whenever you get a n bit instruction, okay, first you will identify how many uh, how many instructions or words are there in a block. You will convert it to power of 2. And whatever is the power of 2, the last power bits, if it's 2 power m, the m bits are going to become, going to represent the instruction. That is basically these 2. So we leave that. The rest of the 4, out of the rest of the 4, we will apply the hash function, okay? And as I told, again look at the power, and if the power is some k, the last k bits are going to become your cache line identifier, or you however you say it. And once you go to the cache to identify which of the multiple blocks that are mapped to that block, we will look at the tag. The remaining bits are the tag. So this is direct mapping. I took a very small example because the one in Carl Hamilton was talking with 2 power 12. I hope this was clear. If you want, I can repeat it again. Was it clear? Guys, someone unmute, please.
Wait, could you
Brush up
repeat like
once.
a bit quickly? Yeah.
You need it once more.
Yeah,
See,
thank you.
basic. So, like, which part is confusing exactly? The calculation part or the ideology part?
The splitting of the instruction into different bits.
So the bits, how I separate the bits.
Yeah.
Okay. See, first you have look at the number of total instructions. Okay. Now here my total instructions is 64 in my main memory. Okay. So it's going to become 2 power 6. That's like the total number of words in my main memory. And each address is going to be 6 bits. So that is why I get 6 bits here. I hope this is clear. Now we look at the given condition of how many instructions we have in one block. As I told, we are only going to map as blocks, not as one instruction. So it's going to be mapped as blocks. So we look at how many instructions are there in one block. We have 4 instructions. Okay. So now, as I told, we do not really care which instruction it is of the block because the block is going to be transferred no matter what. So here we have 4 instructions, 2 power 6 by 4, which is 2 power 6 by 2 power 2, which will result in 2 power 4. That's why we have the 4 bits here. Okay. So basically the 4 bits represent 16 blocks. 0000 is 0th block. 0001 is first block. Similarly, if you write all the combinations with 4 digits, you get each block. Okay. Now we need to know with each block, how is it going to be mapped to the cache? It's basically 0 to 0, 1 to 1, 2 to 2, 3 to 3, 4 to 0, 5 to 1, same thing. Okay. But then we do not really have the time to write all of this like 0, 1, 2, 3, 4, 5, 6. So we use this function. It's very simple. So, like I can also explain it in terms of decimal. Now, for example, if I take 1000, okay, what is 1000 in decimal? It's going to be 8. I hope it's 8, or am I wrong? I'll just check once. It's 8. 1000 is 8. And uh, 8 mod 4 is 0. And we map it to the 0th block. What if it's 5? It's going to be 0101. So we convert 0101 to 5. 5 mod 4 is 1. We map it to first block of cache. That's how it works. But then uh, to identify the number of bits, we see it in binary itself, like in the binary form. As I told, for all the blocks that are mapped to the same block in the cache, the last 2 bits are going to be same. Why? Because the cache size is 4, which is 2 power 2. So the power of 2 determines how many bits are needed to set the cache field. Basically, the bits that identify the block in cache. So we have 4 spaces in the cache, 2 power 2. So the mod is going to give me the last 2 digits of my binary. So the last 2 bits tell me which block in the cache I have to go and search. Now, if it's 8, it's going to be 00. I'll go and search in the 0th block of the cache. If it's 5, it's going to be 0101. So it's 01, which is 1 in decimal. I will go and search in the first block of the cache. And 5 is supposed to be there. Now we are done with the second 2 bits. And the remaining bits are going to be my tag. Basically, it differentiates which of the multiple blocks that are mapped to my cache is the required block. That's all. So basically 0, 4, 8, 12 are all mapped to block 0. But then I don't know if it's which one of it is. It's either if it's 0, if it's 4, if it's 8, I don't know. And that is going to be told by the last remaining tag bits. Was this clear, guys?
Yep. Thank you.
Okay. Okay. That's all. That is all we have to do with direct mapping. Now we will move to associative mapping. Associative mapping is pretty simple, guys. Basically, there is no any restrictions. We can map any block from the main memory to any block of the cache. It is complete freedom. Okay. Uh, an instruction from the processor. So basically, okay. If any block is mapped to any block in the cache, how do we find? How do we find whether if it's there in the cache or not? So basically, I take my instruction from the processor and I take the tag field of that instruction and I compare the tag with every tag in the cache. If my cache has like 128 blocks, I am going to compare the tag 128 times. That's what is happening in associative. So the main thing here is we use space very efficiently because only once the cache is completely full, we use any replacement. Before that, we do not bring in new blocks. We fill all the empty spaces. But then in direct mapping, if my 0th block is already full and I bring my fourth block, it is also mapped to the zeroth block. Now I have to replace it, even though my 1, 2, 3 places of the cache are empty. So it's not efficient use of the space in cache. But then this is very efficient in terms of space. But then it's kind of complex because you're comparing every other tag of the cache. So that is, and it is going to cause delay since you're comparing every other tag. So it has to be searched in parallel. Multiple comparisons has to go on at once, and such search is called as an associative search. So yeah, that's all for associative mapping. Was associative mapping clear?
Yep.
Okay. Now we'll move on with uh, oh shit. Okay. We will move on with set associative. Set associative is like the hybrid of direct and associative. We will okay. Says the combination of direct and associative mapping. So basically, uh, now it is okay. Actually, take it in terms of direct only. So instead of mapping it to blocks, we are going to map it to sets. So all of your memory in cache is going to be uh, mapped into sets. Look at this. Now, the numbers are actually very confusing here. Do not like what to say, try to make sense of everything. But then, so basically, this is one set in the cache. Okay. It consists of two blocks. Can you see my cursor, guys?
Yeah, it's visible.
Okay, okay. So yeah, it's one set. It's nothing like it's the same cache. If it has like 128 blocks, we are going to separate the cache into sets, and each set will consist of two blocks. That's all. Now, instead of mapping my blocks from the main memory to a block in the cache, I am going to map it to a set in the cache. So, if previously what was our in the example previously discussed, my cache had like 4 spaces, right? Now, if I divide it into sets, now how many sets will I have? Two sets I'll have. Zero and one. Or one, okay, two sets I'll have, and each set will have two blocks. That's how it's now. All my instructions are either going to set one or it's going to set two from the main memory. That's all is set associative. So it's basically a limited freedom. So instruction must go to only a particular set, but in that set it can be anywhere. So basically, now if I get a particular address, this address, let's take, we see this 0050 is like it is telling us where in the cache to search. So we go to 00500. But in that, we have two instructions. This tag 000 is compared with both. Here we compare and here we compare with the two blocks in that set. It's not a match. And here it's a match. So we know that this block is found in the cache and it's a hit. So basically, okay, now I'll tell how it's combining both direct and associative. Like if your set size is one, okay, if it's each set containing only one block, then it's your direct mapping. And if your set consists of all the blocks of your cache, like the full map, if you create cache into one set, one whole set, it becomes associative because you're going to compare your tag with every other tag in the cache. So set, set associative is the hybrid of direct and associative. Was this clear or is it confusing?
కొంచెం confusing.
Konja confused. So basically what you do is the same thing as of direct mapping, okay? You will find the hash function and you will map it to one place. So see this at this address the processor has given me, okay? And this is going to be my cache line. Basically it tells me which cache line I have to search. And this is a property of direct mapping. I go to this line directly. I won't search this 0, 0, 0, 0. I won't go here. I'll directly go here. Okay. But then inside this set, inside this space, I have two blocks. I do not know which block I need. So now I'll compare the tag of my address with both of these blocks. And then whichever is matching, I'll take that. And this is a property of associative where you compare the tag with each tag in the cache. Was this clear?
Hey, why though? Like, what is better here compared to?
Because you are increasing your என்ன சொல்றது like see basically you are increasing your chance of a hit because முன்னாடி what you did was if in the 0th place we had 0th block, 4th block, 8th block, 12th block, but only either we had the 0th block or the 4th block or the 12th block, not all, but then when my set size is 2, okay, I will find 0th block and 4th block in my 0th place. Now I have a higher comparison and my chance of hit is higher. What if if my instruction was from the 4th block, okay? But in direct mapping, if my cache had only 0th block, I will only compare it with the 0th block and it will be a miss. But then when my set is 2, okay, I might have my 0th block and 4th block in my set 1 and my needed instruction is in 4th block. So now my chance of a hit has increased because the comparison has increased.
Okay.
Did that make
Yeah,
sense?
got it, got it.
Basically, you're comparing more
Yeah, more comparison, so hit rate is higher.
in higher, that's all. So it all depends on how you place your sets and what instructions you bring from the memory. That's what makes the hit rate more. We'll talk about the hit rate later more. But then, yeah. So for set associative, we will see a problem, and I think that will make things more clear. Okay. Is this visible, guys? I hope it is.
Yep.
So it again, this is a problem from Carl Hamacher. I have just written it clearly. So what's given is each address is 30. It's a 32-bit address. They have given that, and in my memory, each block is going to consist of 64 words. Okay, that's my configurations, and I have a main memory of size 1 gigabyte. Giga is 2 power 30, okay? I have just converted it 2 power 30 bytes. And they told 64 words, and here the word and bytes are same. It was given in the question. I did not write it here. One block is 64 bytes. That's what they had given in the question. So 2 power 30 bytes. So if I divide it by 2 power 6, I get 2 power 24. So I get the number of blocks in main memory, okay? Was this clear?
Yep.
Guys, okay. Now we have the cache configurations. We have 4K bytes. That's 2 power 12 because 1 kilo is 2 power 10. 4 is 2 power 2, so it's 2 power 12 bytes. And again, I am dividing it with 2 power 6 because each block has 2 power 6 in bytes. So I get the number of blocks in cache. Now, my question is to identify the number of bits for each, like how many for instruction, how many for the set field, and set field is nothing but the bits that are going to tell me to put the block in which set. Wait, okay. I think it's confusing. Okay, I'll go in the order. Okay, so is the configurations of main memory and cache clear?
Yep.
Okay. So now, as we already saw, out of the 32 bits, each instruction is okay. Each block consists of 64 bytes. So to address each word of the block, I need 2 power 6 bits because it's 2 power 6. So I'll get 2 power 6 combinations and I can address each instruction of the block. So the 6 bits are going to become word offset. So 32 minus 6, we have 26. We have 26 remaining bits, okay? From that, we have to identify how many goes to the set field and how many goes to the tag. The set field is again the mapping function. Now, how do I come to this conclusion of 2000, 2 power 4? So we already calculated that we have 2 power 6 blocks in the cache. And they have told that each set is going to have 4 blocks. Did I not write it here? Oh, okay, I did not write it here. I am really sorry, guys. They clearly told that each set is going to have 4 blocks, okay? So 2 power 6 by 2 power 2, it's 2 power 4. So in the cache, we have 2 power 4 sets. And we are going to map the address from the main memory to the cache. And we are going to map it to sets because it's set associative. So we have 2 power 4 sets, and thus we have the function as 2 power 4. Was this clear, or should I go once more?
I think this was clear. Thank you.
Okay. So we have the 26 bits, remaining 26 bits. We have modulus with a number of 2 power something. Whenever I told it is in the form of 2 power something, the last something bits of the binary number is going to be your answer. So the last 4 bits of my 26 bits is going to be the set field. Basically tells me to put it in this set of the cache. So my 4 is becoming a set field, and the 26 minus 4 is 22, and these are the remaining, so it becomes the tag. Was this example clear, guys?
Yep.
Okay, so that is all for direct mapping, associative mapping, set associative. Was the 3 clear anywhere? Any doubts? I
No.
can maybe, okay, it's not clear, fine. Now we'll go to the calculations. Okay, basic how hit rates and miss rates basically, because ideally we need a hit rate of 100% so that that ideal delusion of our processor becomes real. Uh, we can be oh, where am I? I'll go to the presentation. Hmm. Hmm. Okay, hit rates and miss penalty. So what is a hit rate? It basically tells you how many of the total attempts you actually find whatever you need successfully in the cache. That is a hit rate or a miss rate. Hit rate is basically number of hits by total attempts, and miss rate is total number of misses by total number of attempts. As I told, to the processor, there is only a single memory, and it thinks that the memory is very huge, and its access time is of the cache. That's what the processor thinks. So how close are we to this delusion? How close are we to this ideal thinking? That is decided based on the hit rate. And for a highly powerful performance, we need at least 0.9 as a hit rate. Uh, if the performance highly depends on the miss rate rather than the hit rate. How? Because the way you handle a miss differs. As we already saw in the cache write and cache read, we saw multiple things like write back, write through, load through. Like all of this had different mechanisms. Now, in the case of write back, write through, I have to, if it's a miss, okay, I will only change it only in the main memory because it was not found in cache. So it was a lesser time. But if it was a read miss, okay, I did not find it in my cache. I have to go to my main memory now. From there, I have to bring it to my cache again. and then from there it goes to the processor. So rather than hitting, the miss rates often affect your performance more. Okay, now you'll see the basic expression how to calculate your average time. This is not the exact time, it's the average time. So H is your hit rate, the number of hits by the total attempts. C is your access time of your cache. This is with the assumption that there's only one cache and one main memory. There's no levels to your cache, just one cache. That's what we think. So first, if it hits, it's the cache access time. So it's H times C. Plus, if it's a miss, it's going to be 1 minus H, because if it's not a hit, it's a miss. So it's 1 minus H times miss penalty is the time access if it's a miss. That's all. So this gives you the time average. Uh, Again, we will see one example. Okay, we will also discuss levels. So basically, our cache can. Am I going a bit fast, guys? Is it fine?
No, this is fine. You can
It's
at the
fine,
right
right?
pace.
So most of the times your cache is of multiple things. So basically you have multiple levels of caches. You have level 1, level 2 caches. This is again to reduce the miss penalty. You reduce the main memory access time, because if it's a level 1 cache miss, you have this possibility of finding it in level 2 rather than going directly to the main memory. That's one use of having level 1 and level 2 caches. And most of the time the level 2 caches size is higher, like your level 2 caches have a size of hundreds of kbs, whereas your level 1 cache is of few kbs, like 1 or 2 kbs. That's how it is. Whereas level 2 is from few hundred kbs to few mbs also. Level 1 cache is on chip most of the times. It's going to be very fast. Level 2 is slightly slower, but it does not impact so much on the overall time, because it is still better than going all the way back to the main memory. We still have something closer to the cache rather than the main memory. That's why levels of caches help. In that case, this will be your equation. Basically, we try to hit in the cache one. If it's a hit, it's H1 C1. If it's a miss, we are going to level 2. So it is a miss in level 1, and if it's a hit in level 2, it's H2, and C2 will be your access time. If it's a miss in both level 1 and level 2, it's 1 minus H1 into 1 minus H2 into the miss penalty, because we have to go to the main memory now, because we don't have level 1 and level 2. So that's why we have added all the possibilities. I hope it's clear how this equation came, or should I explain it once more? Guys, someone please tell.
Yeah, it's clear once again.
Yeah,
Just read pen
clear,
into
clear.
camera.
Okay. We'll see one question. I think that will be the last question, but it's a bigger question though, so I think we'll take time. Like, go through this for a minute. I'll just upload that question here. I did not do it. Just give me 1 minute. Okay, I think it's done. Okay. Huh. So the question is, we have two levels of cache, okay? And the access time of cache 1 is again T, and access time of cache 2 is 15T, and miss penalty is 100T. My hit rate of cache 1 is 0.96, hit rate of cache 2 is 0.80. I think the given is pretty straightforward. Even in the question, it was pretty straightforward. So now my first question is, what fraction misses both in L1 and L2? That was my first subdivision. So now they have given that it is a miss in L1. So that is going to be 1 minus H1. And it's a miss in L2. So it is going to be 1 minus H2. and both, it is a miss in both. So we are taking the and operation. Some we are we are involving some probability here. So we have to multiply because both of these happens. It's not either miss in L1 and either miss in L2. It's both miss in L1 and L2. So we are multiplying 1 minus H1 and 1 minus H2. If you just substitute the values here, this is the answer you're getting. I think if we do the math, 0.008, that will be the answer. Because yeah, 1 minus 0.80 is zero point 0.2 and 1 minus 0.096 is 0.0004. Sorry, actually, okay, 10 is wrong here. It's only, okay, I'm not sure. Okay, maybe do the math, guys. You will get it. I think is the, how this thing came, is it clear? 1 minus H1 into 1 minus H2.
Yep.
Is it fine? Okay. And then they have asked for the T average. T average is the same equation we saw in the slide, H1C1, 1 minus H1, H2C2, 1 minus H1 into 1 minus H2 into miss penalty. We just substitute and this is the final answer. This whole example with the solution is there in Carl Amateur. You can check it out. But only this calculation right here for third subdivision is not there. I did it on my own. Maybe I'll send the solution also in the group afterwards, so that will be clear. So now they have given that what is the time average. The question is what is the time average if there is no miss in L2. So if it's not there in L1, we are very sure that it is going to be there in L2. So basically what this implies is your hit rate of cache level 2 is 1 because you find it every time. It's going to be 1. So if we substitute 1 in the place of H2, 1 minus 1 becomes 0. So this whole term goes away. And we just substitute the rest of the things and you get 1.56 T. Was this clear, guys?
Yep.
Okay. So yeah, we are officially done with cache hits, cache miss, hit rates, miss rates, mapping. Is there any doubts, anything that you want me to go back to again? Anyone, not just Harish, like anyone can tell. Wait, I'll come back. Is there anything? Anyone?
Yeah,
Danya, did you say something or is it clear?
I said it's clear.
Okay. So it's fine. Okay. I think now we can move on to just one more topic, that is DMA. Okay. I'll again go back. Okay. So DMA is nothing but it's direct memory access. So basically, a lot of data transfer occurs within your main memory and your input output devices. So basically, like you just have a pen drive, you plug it into your computer, your data on the pen drive is going to be stored in your memory. So this is a data transfer. And how this takes place usually is that data from the input output device goes to the processor first, into the processor register. From there, it goes to the memory. This is what happens every other time. So the processor is very involved in this process. Okay. And then what processor does is before reading or writing data into the input output devices, it always checks its status like every time. Like it checks its status whether if it's ready to receive or give the information. Okay. This can be done in two ways, polling and interrupts. Basically, in polling is nothing but your CPU continuously checks whether the device is ready. Are you ready? It keeps asking, okay? And it has a status register where it will update whether the input output device is ready or not. Basically, if it's 1, it's ready. If it's 0, it's not. That's the status register. And in this, the CPU is heavily occupied because it keeps on checking, ready, 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 keeps on checking, okay? Then we have interrupts. Interrupts is basic. We have already seen about interrupts in unit 2 and all. So basically, once the device is ready, it gives a signal to the processor that I am ready, and it can start the process. So here the CPU relaxes a bit until the interrupt occurs, but again the CPU is heavily involved in the transfer because it has to receive the data and then store it in the memory, or the same for output. So yeah, um, several instructions with memory accessing. And if it's multiple instructions, okay, we have multiple instruction with multiple memory accessing, and each time the processor has to decide where to save every. So the processor is almost fully occupied during a data transfer. So this is where your DMA comes in uh, handy. So it's nothing but a special unit. It's a special hardware provided to manage data transfer without continuous processor intervention. So basically, you are reducing the load on the processor. How? Basically, there's a unit called the DMA controller. Okay, it is sometimes a part of the input output device interface, or else it is a common unit separately for multiple input output devices. So what this does is basically performs the part of the processor. Um, it provides the memory address where to store it. It gives the required control signals of the data transfer, like it gives the signals to the device to give the data or maybe receive the data, all of that. If it's a sequence of memory, it increments the memory addresses each time for successive words, and it also tracks the number of transfers, how many transfers have happened and all that. But obviously, it is not acting on its own. It acts under the control of a program executed by the processor. Basically, the first step is the processor gives the DMA certain information, the starting address, the number of words to be transferred, and the direction of transfer, whether into the memory or from the memory to the device. This initiates the transfer. Then the DMA controller proceeds to perform the requested operation. It does the transfer one by one. During this time, the CPU can work on other stuff. So the DMA takes full access of the system bus, and then it does the transfer. And when the transfer is completed, it informs the processor by raising an interrupt. Basically, it tells the processor, I am done, and you can finish off this transfer process completely. That's what it says. Um, that's all, guys. I think that's it. DMA is done. I think all the topics that were assigned for me is done. Uh, I'll share all of my handwritten stuff in the group. I hope everything was clear. Anything that I should go back to, anything you guys would like to, or any doubts, why this, why that, all of that. I take it as a no. Uh, no, DMA, I'm not very sure on that, but then I don't think it's a part of the processor. Because as I told, it is a part of the interface, and the interface is not on the processor, I guess. So I'll check on it, Harish. Okay. Um, anything else, guys? Okay, I take it as a no. Dhanya will take over from here. Thank you, guys.
You, Diya. So in 20 minutes, I'll be done with my part. It's just a short part that I'll be covering. So I'll share my screen and start my recording. Wait. Yeah, I'll finish 20 minutes.